Hello Thecloudsguru, welcome to our next video. I want to introduce you to the subnet type based on connectivity and address type. Additionally, I will also show you the IPv6 scenarios in AWS deployment. Let's start. A subnet is a sub-range of IP addresses allocated from the VPC seeder block. A subnet can be directly connected to the Internet. This type of subnets we call public subnets, with private IPv4 ranges and indirectly connected to the Internet. For example, using NAT gateway or egress-only Internet gateway we call private subnets. AWS provides customers with three types of subnets, categorizing them based on IP address types. The first and oldest type is IPv4 only IP addresses allocation. The second type is a hybrid. IPv4 and IPv6 allocation blocks sit in one subnet. And the third type, relatively new, is IPv6 only type. IPv4, hybrid IPv4 and IPv6 only subnets can be public and private. Next, I will show you how to enable IPv6 internet connectivity for your IPv6 only subnets in your VPC. Here's the structure in a dual-stack VPC. Starting from your dual-stack Amazon VPC, the primary seeder is an IPv4, and the secondary IPv6 seeder is used to create the IPv6 only subnets. Now the Internet Gateway or IGW, and the Egress-only Internet Gateway or EIGW, are attached to the dual-stack VPC. Although the IPv6 addresses are global unicast addresses, you can still create public and private subnets, controlling the IGW and EIGW routing and security group configuration. Next, the public IPv6 only subnets route tables have the default IPv6 route, ::/0, with the Internet Gateway as the target. The private IPv6 only subnets route tables have the default IPv6 route, ::/0, with the EIGW as target. Compute resources in public IPv6 only subnets use the Internet Gateway for IPv6 internet connectivity. They can directly initiate an outbound internet connection and accept inbound internet connection. IPv6 endpoints in the Internet, using their IPv6 addresses from the subnet seeder. Note that security groups must allow IPv6 traffic. Resources in private IPv6 only subnets use the EIGW for outbound IPv6 internet connectivity. The egress-only Internet Gateway allows only outbound IPv6 connections to be opened from private EC2 instances to Internet IPv6 destinations and the associated return traffic. And there you go. Next, we will talk about internet connectivity using application load balancers. Previously we have enabled IPv6 internet connectivity for IPv6 only subnets. In this scenario, we will enable IPv4 and IPv6 internet connectivity. Here are a few steps I would like to teach you with these structures using application load balancers. First, configure your VPC ALB subnets for dual-stack internet connectivity by adding the default routes for IPv4 and IPv6. Then, deploy your dual-stack internet-facing ALB and select the dual-stack ALB subnets in the VPC. Your application stack can run natively on IPv6, as the ALB supports IPv6 targets. IPv6 target groups only support IP type targets. The application clients query for the application name and receive the IPv4 or IPv6 address of the endpoint based on their capabilities. For single-stack customers, their stack determines the protocol to be used. For dual-stack-enabled clients, the operating system configuration determines the use of IPv4 or IPv6 for communication. Now, the clients open connections to the application endpoint, using either IPv4 or IPv6. The ALB distributes traffic to the healthy targets in the target groups using IPv6 connections. That's it for the second scenario, and we will talk about network load balancers in the next scenario. So we have conducted on how to enable internet connectivity using application load balancers in scenario 2. This time, I will show you the structure of how to enable IPv4 and IPv6 internet connectivity to your application using network load balancers. Start configuring your VPC NLB subnets for dual-stack internet connectivity by adding the default routes for IPv4 and IPv6. Then deploy your dual-stack internet-facing NLB and select the dual-stack NLB subnets in the VPC. In this time, your application stack can run natively on IPv6, as the NLB supports IPv6 targets. IPv6 target groups only support IP-type targets. The application clients query for the application name and receive the IPv4 or IPv6 address of the endpoint based on their capabilities. For single-stack customers, their stack determines the protocol to be used. For dual-stack-enabled clients, the operating system configuration determines the use of IPv4 or IPv6 for communication. The clients open connections to the application endpoint, using whether IPv4 or IPv6. Finally, the NLB distributes traffic to the healthy targets in the target groups using IPv6 connections. Are you learning? Watch out for our fourth scenario because we will tackle on dual-stack AWS Transit Gateway. I hope you have learned how to enable internet connectivity using NLB from our previous scenario. At this moment, I am going to give you approaches to building global dual-stack VPC connectivity with AWS Transit Gateway. When you attach a VPC to an AWS Transit Gateway, you must specify one subnet from each availability zone to be used by the Transit Gateway to route traffic. For dual-stack support, the Transit Gateway attachment subnets must have IPv6 seeder blocks associated, and the attachment must be enabled for IPv6 routing. Now, Transit Gateway peering connections natively support dual-stack routing. Then from here, update the VPC route tables with the necessary IPv4 and IPv6 routes. Lastly, if propagation is enabled for the VPC attachments to the Transit Gateway, the Transit Gateway route tables will be populated with both IPv4 and IPv6 VPC seeder blocks. Building VPC connectivity with AWS Transit Gateway was, I'm sure, very informative. Moving on to our fifth scenario, we will enable DNS resolution for queries from IPv6 only subnets resources to IPv4 only names. When you create a VPC, the Amazon Route 53 resolver that is created by default maps to a DNS server that runs on a reserved IPv4 address for the VPC network range, +2. For the IPv6 stack, the Route 53 resolver can be reached at the local address FD 00:EC2::253. Without DNS 64, a DNS query for an IPv4-only service will yield an IPv4 destination address in response, and your IPv6-only service cannot communicate with it. To bridge this communication gap, you can enable DNS 64 for a subnet and it applies to all the AWS resources within that subnet. The IPv6-only instance sends a DNS query for IPv4-only endpoint to the Route 53 resolver. In particular, who is IPv4 name example.com? With DNS 64, the Route 53 resolver looks up the DNS record for the service you queried for, and does one of the following. If the record contains an IPv6 address, it returns the original record, and the connection is established without any translation over IPv6. If there is no IPv6 address associated with the destination in the DNS record, the Route 53 resolver synthesizes one by prepending the well-known /96 prefix. Defined in RFC 6052, 64:FF9B:/96 to the IPv4 address in the record. The Amazon Route 53 resolver replies with a synthesized IPv6 address made of the well-known 64:FF9B /96 prefix and the IPv4 address. Thank you for joining along with me from first to the fifth scenario. We have enabled the DNS resolution for queries through the structures given. And now for our sixth scenario. We will use these steps and structures to enable communication between IPv6 only subnets resources and IPv4 only endpoints. You can see that NAT64 is automatically available on your existing NAT gateways, or on any new NAT gateways you create. It's not a feature you enable or disable. Then you will need to route traffic for the well-known 64:FF9B:/96 prefix through the NAT gateway, which performs the necessary translation on the traffic to allow IPv6 services to access IPv4 services outside that subnet. Now, the IPv6 packet from the IPv6 only instance is sent to the NAT64 gateway. The IP is the instance IPv6 address, and the destination IP is the DNS64 synthesized IPv6 address that was returned by the Route 53 resolver. From the known 64:FF9B:/96 prefix, the NAT gateway recognizes that the original destination is IPv4 and translates the IPv6 packets to IPv4 by replacing these structures. First, the source IPv6 with its own private IPv4 address, and the destination IPv6 to IPv4 by truncating the known 64:FF9B:/96 prefix. Then traffic can go to IPv4 only resources in the same VPC. And traffic can go to IPv4 only endpoints in the Internet, if the NAT gateway is public and has an elastic IP associated. Lastly, traffic can go to IPv4 only resources in the private network, over VPN, AWS Direct Connect, VPC peering, or transit gateway. All scenarios are very informative, and I am very excited for all of you because we will talk more about this in our next video about AWS VPC IPv6. For this video, I have discussed the subnet types. Then IPv6 only subnets, IPv6 application and network load balancers, including dual-stack AWS Transit Gateway, DNS64 and NAT64. Before I go, I wanted to share some overview for the next video, where I will show you series of demonstrations on IPv6, and on how to deploy network IPv6 infrastructure using CloudFormation. And there you go. It has been another journey in learning with us. Thank you so much for joining me, and I had a great time in this video. Looking forward to having you in the next to come. And I hope this has been very informative for you, and I'd like to thank you for watching. Don't forget to like, subscribe, and be sure to click the notification bell for you stay updated on my next video. See you next time, gurus.